All right, thank you for the nice introduction, and thank you everybody for coming. I am so chuffed that there are so many people that took time on a Saturday, especially over the lunch hour break, to come and check this out. So thank you everybody for coming. As we just heard, I was signed up to give a talk on the topic of using data science for good, but as I went through and put this stuff together, it really turned into being using artificial intelligence for good. So I hope you are not upset by that slight change in focus. As I'll explain in a minute, I think it's essentially the same thing, and I'll explain some of those distinctions as we go through the talk as well. But I did want to focus on some applications of using data, analyzing data, and using some human-like techniques for interpreting that data and applying them to some real-world problems and some really impactful problems. And I'm hoping that what you'll get out of this session is, number one, a motivation to apply some of your skills to some of those problems as well, and to learn about some of the techniques and some of the resources that are available to you to solve some of those problems as well. So, I was told this was going to be a workshop, so there are going to be some interactive elements to this workshop. If you have a laptop, please do get it out. There'll be some things you can do along the way. Obviously, it's not going to be too complicated because we've only got a short amount of time and we've got people of various backgrounds here. But it should be stuff that everybody should be able to get into fairly easily. If you didn't bring your laptop, don't worry. You'll still get just as much out of the session as everybody else. And I will be demonstrating everything that people do interactively on the screen here as well, so you can see everything that happens. To just give you a sense of the outline, I'm going to spend a few minutes just talking about introduction to AI generally and kind of, my perspectives on how that works. And then we're going to focus on 3 applications and do some workshop elements associated with them. The first comes from a program at Microsoft called AI for Earth, which is about an app which is available on your phone if you have an Android or iOS device, called iNaturalist, which has some pretty cool features, as we'll see, but is also a useful scientific tool for monitoring species diversity. So we'll have a look at that. We'll have a little bit of a break after that so we can get some time to get set up for the interactive workbook sessions. The next application I'm going to look at is based around another app, this time an iOS-only app, called Seeing AI, which is a very cool app which is designed to help people with restricted vision or blind people to help navigate the world. It has a lot of interesting AI-based technologies built into it. And I'm going to take you behind the scenes into the underlying APIs that drive those technologies and let you play around with those as well, both directly from a web browser, and also we'll do some R programming to do that as well. As you might have heard in the intro, I am an R guy, so I'll be using R in my demos. But everything I'm talking about is language agnostic. You can do this from any language you like, whether it be R, Python, C#, you name it, it all applies just as well. Then, when we get towards the end of the session, I'm going to look at a third example, which comes from another Microsoft program called AI for Humanitarian Action. And this is about building a system to help respond to disasters like airline crashes or earthquakes using drones to identify people and wreckage and things like that. That's going to be based around an underlying AI technology called custom vision. And I'll take you through a little example of using that with a fun application, which is a lot more fun to work with than disaster data, called Not Hot Dog. And we'll do that towards the end. I expect that amount of material is probably going to take us about 90 minutes, depending on how fast we go. I do encourage people to ask me questions during the session, especially if you're having any problems with the technology. There is no TA here to wander around and help you, so if you do need help, please just put your hand up. I'll answer the question. That will help everyone as well there as well. And any remaining time we have at the end of the 2-hour block, we can just use for general Q&A there as well. Sound good? Great. So let me just give you a little bit more of an introduction to my background. I'm a data scientist by training, or at least that's what I call myself mainly these days. I studied statistics back in Australia and then the UK, back at a time when statistics was considered a pretty backwater type of a profession. And then there was the big data revolution, and that statistics became data scientists, and then people didn't run away from me at cocktail parties when I said I was a statistician, so that was really cool. But since then, the whole industry has progressed even further. We're now applying these data analytic techniques to much, much richer data sources, things that were previously intractable, like images and sound and text. And that's when things became AI. So I'm going to talk a little bit about what that means in a minute. My primary language is the R language. Just with a quick show of hands here, who is familiar with R? Okay, well, that's great, because many of my examples are in R, so that will really help as we go through things. But I've been working with R since its very inception. I am the co-author of the Introduction to R manual that you might see if you've ever downloaded that from CRAN. And as was mentioned in the intro, for almost 10 years now, it'll be 10 years next month, I've been writing about R and data science at the Revolutions blog, and you can see the link there. And in fact, many of the examples that I'll be giving today, if you search for the relevant keywords on the blog, you'll find lots of additional supplementary materials there as well. For a long time also, I was a big Emacs user, and I was one of the developers of Emacs Speaks Statistics, which is the interface from Emacs to R and a bunch of other languages as well. Although these days I use code rather than Emacs, and I might be using that in some of my demos here today. Feel free to reach out to me if you've got any questions after the session or just want to chat. I'm easily contactable on Twitter at RevoDavid, and also feel free to email me, and my address is on the screen right there. So as I mentioned, I'm a data science, and that's my background. But things are progressing towards artificial intelligence these days. And the way that means, what artificial intelligence means to me is any computer operation, any computer algorithm, computer technique which mimics human-like behavior. And I'm thinking in particular of things like being able to look at a picture and understand its content in some sense, what objects are within it. Or be able to look at a page of a document and not just interpret what words are on that document, but to understand the meaning behind them somehow. Or listen to sound and interpret that into text and so forth. You know, these are what at least I consider the state of the art to be artificial intelligence techniques. Probably also important to emphasize, at least for me personally, what artificial intelligence is not. And it's not a replica of human intelligence. You know, all we really have today when it comes to AI is some kind of simulacrum, what's that word? A simulation of various organs. You know, we have computer algorithms that do a fairly good job of replicating some of the things that the eye does, or some of the things that the ear does. But if there's anything we've learned from neuroscience over the last few decades, is that vision doesn't happen in the eye, and hearing doesn't happen in the ear. All of that happens in the brain. And where we're at right now is we have a good simulation of what those organs do. You know, we've got tools that let us sort of replicate what an eye sees as data and what an ear gets as data. We don't yet have the tools in artificial intelligence to really comprehend what those means in the context of a being's sort of personal experience. All that being said, though, those tools are really, really, really useful. You know, as I mentioned, I worked as a data scientist for a long, long time, where most of the data that we worked with was very regular. You know, just regular tables of numbers, rows, and columns. But the real data that we wanted to get access to, you know, particularly things like unstructured documents and images and video and sometimes audio and things like that, for a long, long time, all of that information was wholly inaccessible to us as data scientists and statisticians. But the way that I like to look at these AI techniques is as a tool for data scientists to extract out information from these previously impenetrable data sources. So if as data I have a bunch of images, for example, of people entering a store, and what I'm trying to track is the number of people that are entering that store, I can now take those images, apply AI techniques which will automatically count the number of faces in each of those images, and then that count is then data that I can use and put into an ordinary regular data store and do ordinary regular data science techniques. But these AI facilities provide me with a new and rich source of data that I never had access to before. And we'll see some examples of that as we get into the applications later on here as well. I'm going to be showing you some pretty impressive things when it comes to artificial intelligence techniques. And they look pretty magical. But one thing that I really want to emphasize, and one thing that I hope you take away from the session today, is that artificial intelligence is not magic. I'm going to go into some of the underlying algorithms that live behind these techniques, and what you'll see is that they're really nothing more than basic arithmetic. It's data to which we apply operations like multiplications and additions and combine them all together to get some kind of result. It's actually pretty simple math when you get back and look into it. The only thing that's different about these AI algorithms that we have today compared to what we had 20 years ago when all this research actually already existed is that we now have, number one, rich sources of data and voluminous sources of data, mainly because of the explosion of sensors and devices that are out there. You know, just the volume of picture imagery that we have is a direct function of just the explosion in the number of cameras that are out there. You know, think of all the cameras that exist on your cell phones, for example. We also have the underlying computing infrastructure that allows us to process these massive volumes of data and do this very simple but very intense mathematical operations on them. So thinking about powerful processors, you know, particularly things like GPUs, which are particularly tuned to doing these kinds of computations. And the actual computing resources, the disk and the memory and the processes associated with that lets us do all these calculations. The cloud in particular has been one big revolution that's made this work, is because now anybody can rent, you know, a cluster of 20 machines that have 20 GPUs and any amount of disk associated with that. And that's something that was previously inaccessible to anybody beyond things like the CIA, you know, as little as 10 years ago. And now anybody has access to those computing resources and can try out these kinds of techniques. One thing about these artificial intelligence techniques is that it's now exposing to analysis these massive new volumes of data. And more often than not, these data are about people, you and me. And I think it is really important that, you know, for us as data scientists and for anybody that is working in this AI realm, to really codify internally a set of principles for working with those data to ensure things like that privacy is respected, that fairness is respected with respect to the decisions that are made on the basis of those analyses, that security is applied to the underlying data, that we recognize things like the data sets that we are using, whatever data you have is biased. Data is collected by people. People have biases, therefore that data is biased. And understanding, most importantly, how those biases in the data are going to reflect later in the decisions that are implemented in your application based on that analysis. I really don't have enough time to get into all the details behind that in this session today, and there have been some really good AI ethics sessions at ODSC this week, so if you didn't catch them in the recordings later on. But do have those principles in mind when you're working with data like these. Microsoft has its own set of principles that applies to working with these types of data and applying AI techniques to them. Number one is to build applications that enable people. So rather than replacing the things that people do, support the actions they do with these AI applications. That all these AI applications and the methodologies behind them should be inclusive and available to everybody. And first and foremost, that the applications that they're used for are ethical. And there's an entire group at Microsoft based out of New York called FATE, Fairness, Accountability, and Transparency and Ethics in Artificial Intelligence, that have a very complete set of principles around these. And if you want to check them out, let me know. I'd be happy to point you to those as well. Anyway, I say all of that just to give a bit of background for artificial intelligence and the kinds of things you might be doing with them. But in this session today, I want to focus on some applications, and specifically some applications around using artificial intelligence for good, for social benefit, for solving real-world problems that affect many, many people. And these all come from Microsoft's AI for Good partnership programs. There are 3 of them. One is Artificial Intelligence for Earth, focused around environmental issues. The second is Artificial Intelligence for Accessibility, focused around supporting people with disabilities. And third is Artificial Intelligence for Humanitarian Action. I will go to those in a little bit more detail, but collectively, these are 3 programs at Microsoft, which together have, I think, around $200 million in funding to support research organizations, NGOs, independent nonprofit agencies, to build solutions with AI around these programs. And I'll give you some more detail about that later on. So the first of our 3 applications here comes from the AI for Earth program at Microsoft. And just to give you a quick intro to that, the whole idea behind the programs in AI for Earth is to empower people and organizations to solve global environmental challenges through technological innovation. There are 4 main areas where AI for Earth operates around sort of building sustainable futures. The first is in agriculture. I'm sure you're aware around climate change in particular is changing the way that crops develop and grow. Being able to use technology to focus around the way crops are planted, managed, harvested, and distributed is going to be really important in the future, really just for ensuring that everybody in the world has enough food. And so there are a lot of projects that Microsoft is sponsoring around that issue. Water is a really big issue for many of these things. Things around ensuring water quality and cleanliness and making sure water is available to all parts of the globe. And also sustainability of water. Again, climate change has a big impact on this, making sure that water sources that are available today that may not be available in the future, we have ways of making water available in those areas. The 4th one on that list, climate change. I've already mentioned a couple of times as well, but in general, analyses of climate data, looking at new ways of collecting sort of inferential data about climate change, things around sort of plants appearing in new areas, changes in soil, those kinds of things. Lots of data that AI techniques can be applied to there and problems that can be solved. But the one I'm going to focus on here in this session today is around biodiversity, using artificial intelligence techniques to monitor and protect species from going extinct and to be able to measure data about where they exist today and how that's changing. I'll get back into the details of that in a second. AI for Earth, I think at this point, has issued more than 160 grants around the world for all sorts of projects. And you can see sort of a map of where they are there. Just a couple I'll highlight here, just in Australia to illustrate. Down in southern Queensland there, they're working with the University of Brisbane, I think it is, to set up audio microphones all around the sort of the bush there, listening for the calls of a particular endangered parrot, and they have an AI technique that can listen to those bird calls and identify that particular parrot and use that to monitor its distribution. The other one here down in Grafton, the little blue dot there, is around using aerial satellite imagery to look at the Earth and use visual analysis techniques and convolutional neural networks to try and estimate the amount of trapped carbon, sequestered carbon, that exists within that Earth and use that as a measure of how the climate is changing. By the way, if you work at an institution that does this type of research and would like to apply for funding, I'll be giving you a link at the end about how you can get into one of these grants. But let's actually go into the example that I have today, which is around an app and a social ecosystem called iNaturalist. So iNaturalist is an online community of citizen scientists. It's been going, I think, for more than 10 years now. Started off as a website, and now it is an online app, or a smartphone app rather, where people can record data on the distribution of the Earth's biodiversity. So there are more than 500,000 registered users worldwide now. They have collected more than 6 million observations on more than 120,000 different species. And the way it works is you can actually download iNaturalist onto your phone. It's available for iOS or Android. And as you're sort of walking around the forest or just going for a walk on a trail somewhere, if you see an animal or a plant or an insect that you don't recognize, you can take a photo of that plant or animal or insect, and it will attempt to recognize it for you. It will use artificial intelligence techniques to try and tell you what species of animal, plant, or insect it is. and it'll give you a recommendation, and that's really cool because you can learn about the things you have. But then that recommendation also becomes data. It's not very good data at that point because it's not necessarily correct, but it's getting better through these AI techniques. And also there's a network of people in this community that review the recommendations and upgrade it to research quality data with their own particular knowledge about those species. So let's see how that works. So I actually used this, I was in Melbourne, Australia just 2 weeks ago, and I opened it up just in the city centre. And one of the things that it does is it just tells you what species people have recorded in your immediate location. And it's kind of surprising just how many different kinds of animals and plants you get when you're sitting in a hotel in a CBD in a big city. So nearby, people had seen magpies, which are the Australian birds. They're very nice. Sparrows, of course. Pigeons, they're everywhere. Eucalyptus trees, as you might expect in Australia. More pigeons and sparrows. Also huntsman spiders, hiding everywhere, even in the big city. There are also various possums and things that were in the local parks. It was kind of very cool just to see what was around when I was in this city. And again, this is just by people using the app, walking around the city, taking pictures and classifying the animals and plants that they saw. Here's another example. A couple of weeks before that, I had been in the UK visiting with some friends in Surrey, and we went for a little walk in a local sort of hiking trail. And as I was going through there were just lots of plants that I didn't recognize. There was a flower, which turned out to be something called fireweed. There was a little butterfly, I don't know how well you can see that, which turns out to be something called a European comma. I had no idea there were so many different kinds of maple. I took a picture of a maple leaf, and it turned out that that was something called a Norway maple. But one thing I want to point out here is you can see that, as I made these I took a photo, and it said to me, this thing is probably fireweed, and I said, yeah, that's probably looks about right. Then afterwards, experts who are familiar with the actual species, they comment and they say, yes, you're correct, you made this classification correctly. Or if you're not correct, they'll put a different classification, and that becomes, if there's enough consensus, that becomes the research quality data. So this is a fun tool that people can use to understand the environment about them as they're walking around in forests or the bush or whatever. And it uses this computer vision tool that sits behind it to do those automatic identifications. But in addition to being a fun app for people to use while they're out walking, the sort of underlying goal behind this whole system is to collect global data about biodiversity. And so as people are walking around, they're actually collecting data about the presence of species in different areas, and then all this data comes together to form a global map of how species distribution is today, and most importantly, how species distribution is changing. The goal, by the way, is that they want to identify 100,000 species offline, and by that it means that this app does work even when you don't have cell service, because there's a model built right into the phone that will identify species, and they want to get that up to 100,000 species that you can use offline with more than 90% accuracy by 2020. All right. So let me explain how this app works, or most importantly, how it worked when it was first released. So you're out there, you're in the woods, you see a butterfly, and you take a picture. So what data have you got at that point? You've got the date and the time that the picture was taken. You also got GPS information, so you've got the latitude and longitude of where that picture was taken. But before the AI techniques were integrated into this app, that was all you had in terms of the picture was just a picture. There was no more information you could get other than just the pixels associated with it. And so what had to happen at that point was, as a novice user, you got no guidance whatsoever. I mean, you could type in butterfly, I think, but that was really, all you had. And it worked the same way in the sense that expert users would then sort of review all the submissions that people had, but it was just overwhelming given the ratio of experts to casual users. They just get all these uncategorized, untagged pictures in that they had to manually look at, compare with other things, and try and associate a specific species with, and just fundamentally it didn't work. There were just too many submissions. As a user, you didn't get any feedback about whether you were right or wrong in your guess, and it just wasn't super useful at that point. So Microsoft worked with the iNaturalist organization to incorporate some computer vision features into this app. And so now, if we follow this path as a novice user, when you take a picture, you actually get some information back. You get some recommendations about what species the system thinks it might be based on an underlying model. And sometimes it's only as vague as, yes, I'm pretty sure this is of genus Acer, when you take a picture of a maple leaf. And sometimes it's super specific. It says, I'm very confident that this particular sort of species. And if it's not confident, it gives you several other options, and you're pretty sure that one of those options are correct. And so as a user, you can then compare what you're looking at with the photos that it gives you, choose the one that looks the closest, and you can feel pretty confident that you're right. And still, that will be referred back to an expert user. Expert users have the same benefit as well. As they're reviewing the submissions, they're pre-tagged based on the AI system that has classified the novice user's recommendation. And the expert users can also compare them to the alternate species that are provided and use their judgment to build up this distribution data. By the way, it uses an artificial intelligence vision model. I'm not going to go into too many details of that today. I'm going to show a different one in a minute. But it's also backed up by a species distribution model, which was developed in R. So using information about where species do exist, combining that with the latitude and longitude and time of day data, they can use that to further improve the recommendations that come out of the vision system. So let's give a sort of a bit more of a work through of how this works. This actually comes from my colleague Jen Marsman from the AI for Good team. She was at a conference in Sweden, I think it was, in Gothenburg recently, and she saw a bird sitting on a boat. You probably can't see it very well on that picture right there. And she took a picture of the bird, and you can see it was on July 14th, 2018. It has the information about the location. One of the things, by the way, you do when you take a picture is like when I was walking through England, I saw a llama. So obviously it wasn't a wild llama, it was in a farm. And you can mark that as being captive or cultivated at that point, and then it doesn't use the location data in order to try and identify it. But this was a wild bird. So in order to provide the location, she just says, get my current location. So that provides the lat-long data for that observation. And there it is. The next thing is once you've provided the lat-long data, it then does some recommendations for what it is. And one of the things you can see it says there is, we're pretty sure it's in this genus, great herons, genus Ardea. Okay, and that looks pretty good. It's pretty close to what Jen saw. But going even specific in the subspecies, you can see the options that it gives you: gray heron, because it's visually similar and seen nearby, and also great blue heron, kokoi heron, and great egret. And the one that matches mostly the one that Jen saw was the gray heron. So she clicks on that and clicks select to confirm that that was the actual type of bird that she saw. And that's actually what gets put into the app. And then then just to finish off that story, she submits that, and then that becomes part of the data that then gets reviewed by the experts who ultimately did confirm that that was a gray heron. All right. So one of the things about why this is working as a diversity monitoring tool is that iNaturalist really relies on having lots and lots of people using the app to gather this data. And by using these computer vision techniques and providing, particularly the novice users, instant feedback about the species of animal, bird, or insect that they're seeing, they're more encouraged to use it because it's really interesting to use it as you're walking. There's also the model that's been developed that's running directly on the phone, so they get instant feedback, even when they're not connected to the internet, which is obviously very common if you're walking way out in the outback somewhere. And it gives people lots of useful information that they can use as they're walking. If you would like to be part of this community, I do encourage people to install that on their phone. It's free. You do need to sign in with a social network or your email address, but other than that, it's completely free. And it's a lot of fun to use, and you can help contribute to this monitoring of species diversity that way. All right. I'll just put this slide up here. We're not actually going to do any workshop just at this point until we get to the next section, but when we do get to the next section, we're going to be working with Azure Notebooks, which is an online Jupyter typing experience for people to work through some of the examples that I've been giving here. If you'd like to look at that notebook, you can go to this URL that's right here. You don't need to be signed in to look at the content, but if you would like to interact with it and actually run the R code and examples that are in there, you will need to sign in. You can sign in just with any Microsoft accounts. So if you have an Xbox account or a Hotmail account, any of those will work. and you can then clone the notebook, which creates your own personal copy, which you can then modify and play with, and you can run all the examples that I have there. Later on in the session, I am going to give some examples of working with some of the Microsoft AI APIs, for which you will need to generate your own key to be able to use. All the APIs have free levels to use, and we're only going to be using the free levels here, so it doesn't cost anything. But you do need to sign into Azure to get access to those keys, and signing into Azure does require a credit card. Like I said, you won't be charged, and you don't need to do this, but if you would like to try it out yourself, that's the way it's going to be doing that. And I have provided a link here, which is for the Azure free account. If you don't already have a subscription, in addition to all the free stuff that we'll be using, it gives you $200 in credits that you can use for anything you like as well. So feel free to jump in on that as well. If you've got any questions, let me know. I just thought while I have this up and people are playing with that, this might be a good pause just to take any questions that people might have. Has anybody tried the iNaturalist app before? Anybody heard of it? Just one person. Okay, great.
I just logged you as an observation.
Oh, yeah. What species am I?
Almost
Oh, good. I'm glad I could identify that. How are we doing?
So when the experts look at this, do they know what the amateur said?
That's right. When the experts sort of look at the classifications, they get the Latin long, the photo that the amateur took, and the amateur's selection. But then they also get next to that all of the classification recommendations the AI system would have given. And so for them, mostly it's super quick because they probably know what it is already. But rather than typing in the species name, they can just click, yes, it's that one, and then review a whole bunch of things quickly.
Might that not create some bias if you already know what someone else said?
It almost certainly does. But that's sort of one of the things about the system is that it's, number one, relying on experts. And become an expert, you have to have a certain number of correct classifications to get to that level in the first place. And there's also a consensus system built into that as well. So when there are multiple recommendations that are all the same, then that sort of changes the strength of the quality of the data at the end of the day. Any other questions? Okay, in that case, let me move on to the next example. Which is around AI for accessibility. Just mainly, this is all about using these artificial intelligence technologies, number one, to provide inclusion for people that otherwise would not be able to use technological systems, to supplement the use of that through artificial intelligence. Kind of the thing about there's a program at Microsoft called AI for Accessibility. Like AI for Earth, it supports third-party research into empowering people with disabilities with tools that support independence, inclusion, and productivity. The vision for AI for Accessibility is to provide a world in which every person on the planet is empowered to achieve more, regardless how they communicate, see, hear, or move. And one of the things that's really driving this and the underlying research behind it is that, we believe and we have found that accessible technology has the potential to drive innovation with more intuitive and personal experiences. And that's not just in terms of making things better for people with disabilities. One of the fundamental sort of design principles that Microsoft has now is inclusive design, designing systems that are accessible to anybody despite any sort of limitations that they might have. And what we found is it makes things better for everybody, for every user. A really good example of this is automatic captioning systems, which we now have for all of our video content. We're required to provide captions for those, and we use a lot of automatic systems for that. And just what we found is that it makes it not just accessible to deaf people, for example, but it also makes it much more accessible to everybody by having access to transcripts that are searchable and finding additional content that way. Now, AI is already being used to deliver meaningful and relevant and contextually relevant experiences. The little thing you can see behind there, that's from an app called Helpicto, which is being used in France to help children with autism to communicate via these pictorial symbols. But I want to give you a little different example today, which is from another app that I mentioned called Seeing AI. And I'll also be looking at the Microsoft Translator system as well. And when you think about how people interact with technology, we do it through our senses and we do it through how our brains interpret things. So, we listen to what apps say. We look at the screen and understand its contents. We speak to our apps. And then we understand, what that content is, and then we get impacted by things emotionally, like we react to things with feelings. And kind of the intuition behind this is think about what happens when any of those boxes disappear. When we don't have the ability to interact with something that can hear or that can interact with something that can speak. But the fact that we now have AI technologies that can do all of these things means that, at least potentially, we can replace those channels rather than with our human senses or our human organs with AI systems and help people to communicate along those channels even when they don't have the capabilities naturally. So the example I'm going to give you here is the AI app, and let me just play a little bit of video to show you how that works.
A man drinks orange juice, adjusts his watch, then opens a door. He emerges from a train station with sunglasses and a white cane, then walks along a London sidewalk.
I'm Saqib Sheikh. I lost my sight when I was 7, and shortly after that I went to a school for the blind. And that's where I was introduced to talking computers, and that really opened up a whole new world of opportunities. I joined Microsoft 10 years ago as a software engineer. I love making things which improve people's lives. And one of the things I've always dreamt of since I was at university was this idea of something that could tell you at any moment what's going on around you.
He taps sunglasses to take a picture.
I think it's a man jumping in the air doing a trick on a skateboard.
He types out a computer, then sits with colleagues.
I teamed up with like-minded engineers to make an app which lets you know who and what is around you. It's based on top of the Microsoft Intelligence APIs, which makes it so much easier to make this kind of thing. The app runs on smartphones, but also on the Pivot Head smart glasses. When you're talking to a bigger group, sometimes you can talk and there's no response, and you think, is everyone listening really well, or are they half asleep? And you never know.
He taps his sunglasses.
I see two faces, 40-year-old man with a beard looking surprised, 20-year-old woman looking happy.
The app can describe the general age and gender of the people around me and what their emotions are, which is incredible.
In a restaurant.
One of the things that's most useful about the app is the ability to read out text.
Hello, good afternoon. Here's your menu.
Great, thank you. I can use the app on my phone to take a picture of the menu, and it's going to guide me on how to take that correct photo.
Move camera to the bottom right and away from the document.
And then it'll recognize the text. Read me the headings.
I see appetizers, salads, paninis, pizzas, pastas.
Years ago, this was science fiction. I never thought it would be something that you could actually do. But artificial intelligence is improving at an ever faster rate. And I'm really excited to see where we can take this.
In a park with a woman.
As engineers, we're always standing on the shoulders of giants, building on top of what went before. And in this case, we've taken years of research from Microsoft Research to pull this off.
I think it's a young girl throwing an orange frisbee in the park.
For me, it's about taking that far-off dream and building it one step at a time. I think this is just the beginning.
The Microsoft logo appears.
So I've met Saqib quite a few times now. He's an engineer for Microsoft based out in London. Super inspiring guy. He had this idea at 1 week, which is like every year Microsoft has 1 week where all the engineers get together just to hack on whatever they wanted to do. And Saqib had this idea of like, what if we had these AI and vision systems, which at the time were just in research, and we could put them onto a smartphone app, and as a blind person, I could actually understand what was around me in a way that you really couldn't before. And they put together a prototype just in those 5 days. And then they hooked up to the pivot head glasses you saw, so you touched a button and it just ran what was on the app. And it was fun and it worked for them. But since then, it's become a real thing. Like this Seeing AI app has been out on iOS now for, I think, for 18 months. Got amazing adoption from the blind community. Like I've heard people like things like use the app to play Magic the Gathering so that the app will tell them what cards that are on the table, things like that. People use it to watch videos, like they put their phone on a tripod in front of the TV, and then the phone is just describing what's on the screen so they can sort of understand more about what's going on in the shows. Like really, really inspiring stories about that. You can download it and try it right now if you like. I encourage you to do so. I already have it on my phone. I just took a picture as you guys are watching that video, and you probably can't see it, but it's a picture of the room. And it automatically comes back to me with a caption, a group of people sitting at a table in front of a laptop. And, it does all sorts of other things as well. I can do things like, I'm going to put it in face mode now, person mode. Where's person? There we go. And I'm going to flick it over to do a selfie. And as I click on the thing there, it does a photo of me. There's me looking strange. And it says, oh God, 52-year-old man with gray hair and a beard wearing glasses looking natural. Pro tip, having a beard, and particularly a gray beard, adds 10 years. So, so play around with that. The reason I bring that up is because, this app is just a really, really good demonstration about, how these AI techniques can help, in this case, blind people and people with low vision sort of do things in a really, really practical way. And it's just a really good demonstration of the value of computer vision. The app has sort of various tools built into it, things like short text. So if you're walking around and there are signs, like road signs or street signs, as you hold them up, it will just speak when it sees text, and that's a useful way of navigating. Document you saw in the video, being able to orient the phone over a document on the table and then describe all the text within it, like for a menu. Product we'll see in a minute, that's looking at barcodes. Person was the one I just tried. You can point it at a group of people. It'll tell you how many people are in the frame. And then if you click on the screen, it will give you more detail about their age and so forth. Scene was the one where I took the photo and told us of people looking at laptops. And there's also a really cool currency thing I'm not going to show here, but one thing I didn't realize is blind people, particularly in the States, often get ripped off by people giving them a $5 bill when it's supposed to be a $20 bill. And this app, you can just put money in front of it and tell you what it is. Very cool. Anyway, so what I want to do in this workshop session, we're going to get interactive now, is show you and let you play with many of the APIs that exist within something called cognitive services to do these various techniques. So the way these APIs work is you just need to get an authentication key first of all, and then given that key, you can, for example, provide it with an image, and then it will come back with an analysis of that image. Lots of information about how many faces are in there, what expressions those faces have, what other objects are in there, all sorts of things like that. And we're going to play around with it. I also, as I was putting these slides together, one thing I realized was this is also a really good example to show you the difference between what I like to call the 3 different stages of AI. Most of the ones we're going to be looking at here are what I call pre-trained AI. So this is where a big research team, in this case Microsoft Research, has taken probably millions of images in the case of a vision system. People have tagged those images with what objects exist within them, and then an artificial intelligence model, in this case a convolutional neural network, has been applied to all of that data to actually provide a mapping between new images and the objects that exist within them. With this pre-trained AI, you don't need to worry about any of that, though. All you need to know is I need to provide a picture, and it's going to give you back information about the objects in that picture based on all that research. So it's using these intelligence APIs, but all you need is the data you're going to use for what we call inference in the AI world, the thing you actually want to get information from. The next level after pre-trained AI is what I call enhanced AI. So with our vision system, if our vision system is designed to identify apples and oranges but isn't designed to identify bananas, there's nothing you can do. If I put a banana in front of the camera, it's going to say apple or something else. But there are ways you can actually augment these pre-trained AI systems. You can provide your own additional data. In this particular case, pictures of bananas. And without too much effort, and in particular without too much data, you can augment that vision system so it learns about bananas, even though it's already learned about all those other things from the research team. I'm going to show a couple of examples here of using enhanced AI as well. But sometimes that doesn't work either. You need to build an entirely new system from scratch to recognize a completely new class of objects or a completely new different sort of data interpretation. And that's when people use developer tools, things like TensorFlow or PyTorch, and brand new data sources, and build brand new types of AI models using these frameworks to solve brand new problems. That does require a lot of expertise. It requires lots of data, and it requires some pretty hefty computational resources some of the times, but still, that's something that a lot of people do, and it's the way people are pushing the envelope forward in terms of artificial intelligence, and many times a lot of these bespoke tools go around to become pre-trained AI that become available in services as well. I bring that up because we're going to show all three stages of artificial intelligence in this particular example here. We're going to start on the left-hand side here, just using the pre-trained AI, and as I mentioned, that's in the Microsoft side, that's with Microsoft Cognitive Services. There are similar things available with other providers as well. They're into 4 different categories: speech, vision, language, and search. I'm going to focus in this example mainly on the vision APIs that are available to you. All right. So this is the same slide I had up at the very beginning. If you want to follow along with me as I go through this demo, you can visit Azure Notebooks, sign in, and have a look at that particular notebook. I'll show you how to do it in just a second, but I do ask you to clone that notebook before you use it, because then you can actually make some modifications and play with it yourself. And also, if you would like to play with the Seeing AI tool, that's what you need to search for in the App Store. And these are the 2 workbooks that we're going to be working through as we go through this session. All right. All right, let's go back. So I'm going to go to, there we go. So this is the webpage that I mentioned, notebooks.azure.com, David Smith, Libraries AI for Good. All right, let me just make sure I'm still signed in. I'm just going to refresh. It does log you out after a while. There we go. Okay, so there's all the information that you have here. Once you've signed in, one thing I'll ask you to do is go in here and click the clone button. Okay, I'm going to need to give it a unique name because it's going into my own thing, but you can give it any name you like. Click clone. That's just going to make a copy of all those materials. In your case, in your own library. In my case, it's going to make a copy of the library. All right. I'm going to start here with this one, calling the AI behind Seeing AI. Let me see if I can make that a bit bigger. Okay, can everybody read that at the back? Is that all right? Good? Okay, great. All right. So we're going to be using the various cognitive services tools that are available. This first link here, the Cognitive Services APIs, I believe that is the right one. So this is actually an index to all the different APIs that are available. As I said, we're going to be focusing on some of these computer vision ones and also some of the face ones. But if you would like to explore, for example, all the speech APIs, for things like doing speech to text or text to speech or understanding content within speech, they're all there. Language is mainly the translator stuff. We'll be talking about that a little bit in the next section as well. I'm not really talking about knowledge or search at all, but these are basically around the ideas of taking massive volumes of unstructured data, documents, and so forth, and being able to ask questions about the content that exists in those. All righty. So as I mentioned, if you want to sort of try out these on your phone and you have an iOS phone, try the Seeing AI app. It's going to be using all these same APIs that I'm going to be about to tell you. All right. As I mentioned, when you use these things, we're going to need to provide some data for it to analyze. And in this case, because we're working with vision, that's going to be pictures. You can use pictures from your phone, but to do that, you're going to have to upload them to your laptop first and then copy them over into the API. If you just want to try some pictures on the web, you can also just provide the... I just broke that. All right. You can also just provide the URL of a picture on the web, and if you just want to find some pictures to play with, there's a neat link you can use to get a random page from Wikimedia with an image in it. That's not a particularly useful one, that's a chart. But if you just sort of keep on... Okay, that doesn't work. I thought you could do that. Let's go back here, click this one again. Actually, I have it here. There we go. This one. All right, that's the link I'm looking for. There we go. You just keep on clicking this link, and it'll just keep on generating random images from Wikimedia Commons. And so you can just keep on doing that until you find something that looks like it might be fun to analyze, and then send that over to the API. I've already done that a few times to give some examples in the workbook here. ImageNet is another good source of images if you want to play around with it. One of the nice things about images is if you can do a search for bananas. Okay, and it looks for relevant categories, and there you can find all the images that happen to exist in ImageNet for bananas. So this is actually a collection of images that's been put together over the last 10 years or so, mainly for research purposes. A lot of the popular pre-trained vision systems, you might have heard of things like AlexNet or ResNet, were trained on this data. But it's an interesting source of data you can work with yourself. And of course, you can use Google Images as well, just to search for an image of any type. One of the things about Google Images, though, it's a bit tricky to get the actual URL of an image. You've got to click through to it first. They change the way it works, but as long as you have a URL that goes straight to a JPEG file or a PNG file, you can use that. All right. So let's have a look at some of these APIs. I'm going to start with the computer vision APIs. And you might have seen me earlier on just use the person feature in Seeing AI. You can hold the camera up to a group of people. It'll tell you how many people are there and their approximate ages and apparent genders. Or you can click on an image and it'll tell you lots of detail about them, like their emotions. And that's all done using the Face API, which will detect one or more human faces in an image and then return information about the location and attributes of those faces. So if you want to play with this, I got the link here. You can go to the face detection page on Microsoft Cognitive Services. All right. And you can see, the text is probably a bit small, so I can make that a bit bigger. That might be a little bit bigger. And you can see there's a bunch of sort of example images that they provide here. But when you send the image over, what you get back is a JSON object. And you can then interpret that JSON or parse that JSON object in any language you like. And I'll give you some examples using R in a bit. But what it comes back, what it does is it detects all the faces that exist in that picture and gives you things like rectangles for each of the faces that exist. So a bounding box, which is represented by this purple box over here. We get information about attributes of the face, like whether the person is bald, the hair color, and we get confidence scores. This is mostly brown, according to this particular thing. Whether they're smiling, how their face is posed, apparent gender, and apparent age. And like I said earlier on, that's not necessarily the actual gender or the actual age. Facial attributes like mustache, beard, sideburns, whether they're wearing glasses, if they're using makeup. And then also an assessment of the emotion of the face in 7 different categories: anger, contempt, disgust, fear, happiness, sadness, and surprise, or they may be ranked as neutral. And each of those comes back as a 0 to 1 score, according to how much the face is representing each of those emotions. And this particular example is just 1.01 happiness, so 100% happiness and nothing else. And lots of other things as well, whether it's blurry, the exposure of the image, and also lots of detailed landmarks of the face, like the exact position of the pupils, the corner of the mouth, eyebrows, all that kind of stuff. And that's mainly used in sort of more advanced face recognition type of applications as well. So let's have a look at a few examples. Close that window, don't need that one. So I've got a picture here of a Sikh man. It comes from Wikimedia. If I go back to the Face API, I'm going to pump that URL in as the image. You can also upload a file directly from your laptop with this browse button, but I'm just going to use the web-based one. So it comes back with the Sikh man, identified one face. By the way, if there are more than one faces in the JSON, you get a JSON array with one element for each face that it finds. The rectangle, face attributes. In this case, we've got not smiling, gender male, age 67, facial hair, mustache, 90% mustache, yes, 90% beard, 90% sideburns, no glasses, and emotions, this guy is neutral. Give you another example. Oops, go back a slide. We have, actually, let's do this one, a woman performing in a concert. Oh, that did not work very well. Try this again. Don't know why that one didn't work. Let's try this one instead. Copy link address. There we go. Don't know why that last one didn't work, but here we go. This is, I think, Olivia Munn, actually, at a comic book store. Only identified the one face. It hasn't identified this half a face here or the one facing backwards. Same kind of things. We get information about hair color brown, smiling, gender female, age 36, no facial hair, no glasses, using makeup, and this one is, again, a happiness 1.0 for that particular face. So play around with that. Feel free to try your own images. As I said, you need to upload them to your laptop. Or you can just use the Seeing AI app and just point it at yourself. And it's doing exactly the same thing, but just condensing this JSON data into a sentence, which then gets read aloud for the hearing impaired people. Vision impaired people, sorry. Now, as I was going through that, you saw the emotion recognition was included in the Face API result in JSON. And there's also a nice little tool on that same page that just lets you focus in on the emotion recognition, which is fun to work with as well. So I can just click on the emotion recognition demo here. And I think I have something like a grimacing woman here. These were just random images that came up in Wikimedia as I was clicking the button to refresh it. And go back to emotion recognition. Submit that. Okay, so we've got one face detected in here, and now we're just returning only the emotion detection stuff here. So the face rectangle is highlighted on the screen here, and she's coming here as 32% fear, 8% contempt, 13% neutral, 30% surprise. It's kind of a complex emotion. All right. Close these pictures and go back to the thing. All right, so play around with that. The other thing I wanted to show you too in terms of, this is not now the Vision API, this is one of the text APIs, was for documents. You saw the example of Saqib having a menu in front of him, and then the phone was guiding how to position the phone to take a photo, and then it would analyze the contents of that menu. I'm going to focus on that second part of the problem here, which is analyzing the contents of the document. And there are three tools that are available in the app: short text, document, and handwriting. I'm going to look at just two of those: extracting printed text and handwriting. And that's with the OCR service, which is another API that you can call out to in computer vision text. This is the example they give here, just some handwritten stuff, and it gives back the text that it pulls out. But I'm actually more interested in looking at the JSON result, which is for every individual piece of text that it finds in the image, it comes back with an element with a bounding box. The bounding box has 8 numbers in it because it's the 4 corners of the rectangle, and that rectangle can be tilted. It doesn't have to be aligned to the edges of the document. And then the words that it finds, and it does that for every piece of text it finds in there. So to do that with something a bit more interesting, here's another image I have. This is a business card from a House of Representatives in Greece that came from Wikimedia. I paste that back into the tool. You're going to say, there we go. So now you can see all the pieces of text that it's found. Its name, Andreas Asiatis, member of the House of Representatives, address, phone, so on and so forth. And if you want to know where they were all found in that document, in this case the image, all those bounding boxes are associated with the one piece of text that it finds. Basically, it looks like any piece of text that's contiguous, in a straight line, becomes one element of the JSON result that you can extract from that. That's all there as well. I just want to give you one other example just to show you some of the difficulties you might have with it, and that's with this White House menu. So this is a menu that came from the Nixon White House in 1974 with a dinner with the Emir of Saudi Arabia, or King Hussein of Jordan it was. All right, and if I plug that into the API, it's doing its analysis. Okay, and just have a look at the order in which things comes in. It says dinner, and the next thing is Schloss, which was over here, and then Cold Columbia River salmon on Bellevue, then Johannesburg. You can see what it's doing. It just goes down the document from top to bottom and finds contiguous pieces of text, but it doesn't have any sense of there's a column over here and a column over there and different bits of text here and there. You can also reconstruct that because you get the locations of all the text on the image, but just be aware it's not reading it like a human is reading in that context. It's just finding bits of texts that you're then going to use in whatever thing you want to do after that. There's also a specialized tool in there. That's OCR API is really designed mainly for printed type documents. It does detect sort of handwriting like fonts, as you saw in that first example that came up there. But there is a beta tool available which will let you try and analyze your own handwriting. It's actually what's used in the Microsoft OneNote app, which has a pen and you can scribble on it, and it does a pretty good job of getting that out, and that's using this handwriting API. And you can play with that as well with the handwriting recognition tool. There we go. So there's sort of the default example that comes in there. But just to give you some examples, I'm actually not sure what this image is. That's not it. Where did it go? There we go. So just a few words written on a notepad. We push this into the handwriting tool. Okay, you can say, hello, this is ODSC analytics, I think, but it's come as is analytics. And it thinks this vertical bar is a 1, so your mileage may vary. But I also thought this one was cool. This is apparently a letter that a child wrote to a service member in 1991. And when I plug that into the API, this child has much better handwriting, and as a result, it does a lot better in actually extracting out the text for it. Dear Lieutenant General Boomer, May 30, 91, thank you for everything you did, for bringing our father, I don't know if that was spelled right in the letter or not, back from Saudi. Didn't quite get Saudi Arabia out of that. And you very much, even though my dad didn't go there, he went, and so on and so forth. Sort of didn't quite get this strange TH out of thank you, so I didn't pick it up, but does a fairly good job of converting that to text. Any question? Yeah. Yeah, so the question is why there are two different APIs, like one for regular type and one for handwriting. There's two reasons for that. One is kind of as our research teams have been introducing new sort of capabilities, rather than sort of messing up an existing API that's in production, typically they produce a beta API that's devoted to a specific task, and then eventually this will be rolled into the main API. But as things stand right now, if you know what you're getting is handwriting, because, for example, you're working with a handwriting app that uses a pen, this is going to work out better than the AI trying to, like, it's basically the search space, right? If it thinks it might possibly be printed text or handwriting, it's not going to do as better if it knows a priori that it's handwriting when it does this analysis. So if you put this same image back into the regular one, in fact, we could probably even do that. Yeah. And how did you find it? So you tried it in both. How did you find it when you put it into the regular one?
In the regular one,
Yeah.
it didn't spell psychic right.
Yeah.
The handwriting did.
That's right, yeah. So the handwriting ones was able to spell the words correctly, but the regular API didn't pick it up, and that's exactly the thing. So when you know it's handwriting, the handwriting API will do better. If you're not sure, just put it into the regular OCR API.
So what's different about the code?
Oh, it's a different underlying model. So the handwriting API has been trained on a bunch of handwriting specimens, whereas the regular OCR API has been trained on a much broader class of data. So it's a different underlying neural network that's doing the detection. And we'll see actually more examples of that at the end of the session when we do some custom vision stuff. The actual sort of neural network that you're using and the data it's trained on makes a big difference. And if you can use a neural network that's been trained on similar kinds of data that you're trying to analyze, you'll invariably get better results. That's a really good question. Any other questions? All right. So I just want to wrap up this little section with the scene description feature. You remember I took a picture of the screen and it said a bunch of people sitting on tables in front of laptops. So this is the tool, the underlying API that drives that capability. So there's an analyze an image tool. So you give it a picture and it'll come back with a natural language description of the scene, a list of objects detected in the scene, attributes of the image, things like is it black and white, is it a line drawing, is it clip art, also a flag about whether the scene contains racy or adult content. So these are two extremes, mainly used for things like content filtering, people that submit images in message boards and that kind of thing, so you can automatically filter those out. Detects faces at a sort of more limited depth than the face API does. It'll just tell you the number of faces and their apparent age and gender, but then you can pump that into the face API to get the details like emotions out of it. It also does things like color analysis. What's the dominant foreground and dominant background color. This is mainly to do things like if you have a picture and you need to put it on a screen and you're not sure what background to have, it'll help you make that kind of decision. So anyway, let's play with that a little bit. Let's go to the Analyze an Image tool. There it is. That's the default image, but let's get something a bit more interesting. Let's start off, let's say, with this husky, because it's cute. There's a picture of a husky. Put that image in there. So this is a bit different to the face API. And then what we get back now is a description of the object associated with tags. And these tags are basically every type of object that it found in there. So I can see there's a dog, it's a fence, it's outdoor, the dog is sitting, there's grass, front looking, the dog is looking at something. All the kinds of sort of tags that are associated with that particular image. And then there's another AI system that puts those tags together to assemble it into a sort of sentence description. And this one comes back as a dog sitting in front of a fence. And that's exactly what the Seeing AI app says to you when you use the scene feature, just grabbing that little bit from the API. Another important thing to note is that it comes back with a confidence score too, and this is really important. In this particular case, it was very confident about that description, 96%. But once you get below about 80% confidence, things can get a bit dodgy, and it can start trying to describe things that aren't there or just not very well. So my advice to you is if you're relying on this, just be very aware of that confidence score and be sensitive about how you use it when it gets below around 80% or so. And we'll see some examples of that, I think. You also get confidence scores associated with all of the tags as well. So it's very confident there's a dog there. It's very confident that it's a fence there. And sort of the mammal it's just not very confident with. That's not a great example, but there are other things there as well. I'll give you another example. Actually, this is a good one, pyramids. So this one, there we go. So it's archaeologists in Egypt. So you might be on vacation and taking that picture with the app, and it might come back with a description of a group of people on a beach. All right, so that's obviously not correct. And this is another good example where the underlying training data obviously did not include many examples of archaeologists working around the pyramids in Egypt. So I just had no context to provide that information. And so as a result, the confidence was low. So don't rely on those those captions in those kinds of situations. And in fact, as I look at this, pyramid doesn't even appear as one of the tags. So probably the underlying training data, there were no pictures in there that anybody had tagged as pyramid. Otherwise, it's likely it would have come up as one of those tags. Yeah, question.
Does it return any bounding boxes so that you can say, okay, I want to see what in that photo is?
Yeah, the question was, does it return bounding boxes so you can see where those objects appear in the photo? And the answer is yes, it does. Unfortunately, this little demo app doesn't produce the whole JSON, but I will show you a bit from R, an example of grabbing all of that stuff in a second, but it is there. Yeah. Okay. All right, so all I've done so far, I've kept things simple deliberately. We've just gone to a website and we've provided a URL of an image, and that's gone back to the service and run the API and then brought the results back to a web page. And you could build something like that yourself. If you want a website that did exactly that, it's really, really easy to do. But I also wanted to give you some examples of how you would incorporate this into some of your more regular data science work. So I want to give you some examples now of using this exact same API, the image analysis API, but doing it from R. And like I said earlier on, it doesn't have to be R. It could be Python. It could be C#. It could be anything that you can do an HTTP post request from, which is pretty much anything. So let me show you some examples of how that works. So we're going to go now, going back to the workbook library. I'm going to go to number 2 here, which is Computer Vision API with R, Python notebook. Let's grab some more water. So this is an R script that'll let you explore the Cognitive Services Vision API via its REST API. So what I'm going to do is, you saw that thing where I clicked on a link to get a random Wikipedia Commons image. I'm going to do that as an R function, which is actually going to interface directly with the Wikipedia Commons API, which is very powerful as it turns out. It's super confusing. But once you get it figured out, it's actually a really useful source of images. I've written this all up in a blog post so you can see all the details of how that works there. You know how to use notebooks. We've talked about cloning already. All right, this is where we get to the bit that if you want to run this stuff yourself, you're going to need to an Azure key. And I'll run through that all a little bit as well. Actually, I'm going to need to do this right now. So let's actually run through some of the steps here to get myself set up. So first of all, this is me logging into the Azure portal. So I already have an account, so I'm logged in. So first thing I'm going to need to do is create a resource groups. A resource group is like a bucket to collect, collect the virtual machines, keys, you name it. I mean, the nice things about research groups is that it just helps you organize all the resources that you create within Azure. So I'm going to add one for here called AI for Good. And I'm going to create it in the South Central US region. It doesn't really matter too much where you create it. This represents the data center, and there are 30 or 40 of them around the world. The reason I'm putting it in South Central US is because the captioning API is currently in beta and is only available in that one region right now. One thing you might have seen is it's all a bit blurry up here. The reason for that is because I've got a mask turned on, which automatically blurs out all of my keys, so you guys can't see them. But if you see blurry, that means there's a key underneath there that I'm grabbing. All right. So I just created the resource group. Let me just refresh so I can see that. AI for Good. Why did I do that? AI for Good. There we go. All right. And the next thing I need to do is to create a computer vision key. So I'm going to create a resource. And I can go down to AI and machine learning, computer vision. Okay, so the key, AI for a good vision. So I just need to give that key a name. Goes into my subscription, location the same as before. Pricing tier, as I mentioned, all of these AI services have free tiers. The only restriction is you typically can only call them a certain number of times per second. If you go over that, it will just return an error. But as we're just sort of playing around with things, that's not going to be an issue at all. But this free tier lets me do 20 calls per minute, up to 20 calls per minute. That's the rate limitation, or 5,000 calls in a month. And I'm going to put it in my research group, AI for Good. Create. All right. So in a second, it's going to pop up with that. All right, so that's been created now, and I have this key here called AI for Good Vision. And I'm going to click on the keys button here, and in your screen this is all blurry, but what I have now is two keys. They're just two copies of two instances of the same key. I'm going to copy that into the clipboard, and I'm going to use that in a second when we go into R. All right, so we've done all those things, created authorization keys, we're all good to go. The next thing I need to do is edit a file I put in here called keys.txt just to house the keys. So you can click on that and do edit file. You can also download the file and edit yourself. So I just put the region here is going to be South Central. And this file format isn't anything specific to Azure. I just wrote an R function that's going to read this in as a table and grab these keys. And that key that's there now is just a dummy key. And you'll see this now, but I'm going to go ahead and pull the key in that I just grabbed from Azure. Save that. All right, let's go back to our R script. All right. So now I'm going to run this in R. All I need, it's pretty simple. I just need the tools library and Hadley's HTTR library, which is going to let me interface with the API. I'm going to read in the keys from that keys.txt file, then extract out the vision key that I just put into the file. All right, and it's just confirming that I'm at that South Central US region, so everything worked. I'm just creating a vector in R with a bunch of example images from the web that we can play with later on. That's done. All right, and now I'm going to write, I'm just going to interface with the API manually. So I'm going to grab one of those URLs, which was the second one. It's a picture of an elephant called Queenie. There are parameters you can put into the API about what kind of information to return back in the JSON. So when I get back the description, all the tags of the objects, the categories of the objects, and any faces that exist. You can also have it identify landmarks and celebrities. It's been trained on images of those things, and it will return that information back if it finds them. But this is the important bit. All we need to do is define the URL of the API, which is just about collecting together the endpoint URL and the parameters we just defined of what we want to get back from the JSON, and then call out to the API just with a post query using the HTTR package. And then what we get back is a data frame that contains all of the content that came back from the API, and then we're going to extract out a couple of things from there. I'm going to run that now, so this is actually running live. All right, let's actually look at the image. It's an old black and white image of a bunch of people riding an elephant through a fence. But this is actually another good example of things not working too well, because it comes out as a man riding a horse through a fence, with actually a fairly high confidence of 89%. So it didn't do too well in that particular one. But one of the interesting things about that is to the question earlier on about can you get the bounding boxes, the individual images. We actually print the entire data frame object that the post query gave back. So this is basically all of the JSON interpreted as an R list, essentially. We can have a look at what we get here. We get all the categories. So categories outdoor, tree, outdoor, mammal, animal. So horse, it came back with confidence 34%. But if you look further on, I think one of the tags, as I recall, it actually does come back with elephant as a tag. So I'm not quite sure what's going on there. You could have identified there was an elephant in the picture, but the caption included a horse instead of an elephant for some reason. I'm actually not sure about that. I need to ask some questions because it comes back with these things up here. So this first set, the tags here, are the actual objects that are detected in the image, and it does come back with confidence scores for those. But then we have this description field. So this is kind of the underlying data that it uses to generate the caption. and those don't have confidence scores about them. I'm not quite sure why. I might have to ask the team about that. But that's just basically the data that's used to generate this description here. And for some reason, it went with horse rather than elephant because it had both in there. All right. Okay. So anyway, that was just an example of sort of directly interfacing with the API from R. But of course, we typically want to sort of package that up into our own function. So what I've got here is a function that I've defined in R called image_caption, which basically does what we just did manually. Given a URL, it'll send that URL to the API, extract out the JSON response, and then just extract out the description part of that. So we can go ahead and define that function. And then now I have a function in R that I can run with any kind of image I like. So image caption of this one. It's running that live now. So it says a large white building with Sacre-Cœur, Paris in the background. And the actual image that I passed into that with this one. So I think it's interpreting this wall here as the building. And then there's Sacre-Cœur indeed in the background there. But of course I can pass any kind of URL I like into that function. So let's actually grab out some other examples here. Oops, where's my code? All right, so let's try this one. Copy that. Go back to my function. Paste that in there. All right, so a chair in a room. And what is it? It's not quite a chair. All right. But anyway, you can play around with that, provide any kind of images you like and see what comes back from it. I did also define a function here in R that will generate a random image from Wikimedia, just as we did before with the browser. And now I can just grab a random image and then run that image caption on it. Let's see what we get. All right. So Wikimedia Commons description. This is actually what Wikipedia says it is the death of Buddha. The image caption is a stone statue of a person. And the actual picture was a stone statue of a few people. So play around with that. Get as many random images as you want. But I just really did that as an example of how you can access these APIs programmatically and how you can encapsulate these APIs into larger functions and use that in your own work. All right. Any questions about that before we go on? Because we're going to go back into slides in just a sec. Question here? The question was, when will Seeing AI be available for Android? I have heard it is under development, but it has been for a while. I don't actually know when it will be released. I do know one of the reasons why they're focusing on the iOS version, though, is because iOS has a whole bunch of operating system level features built in, which are really useful, apparently, for low vision users, which Android doesn't have. And so most of the blind community is on iOS, which is why they put all their focus into that one. Yeah. Another question back there, yeah? So the question was, are we using deep learning to identify the images, but which images? Oh, yeah, which technologies are being used on the back end? Yes, it is deep learning that is being used to identify the images, generate the captions, generate the tags. It is, I believe, a form of convolutional neural networks. It all comes out of Microsoft Research. And I'm actually going to go into a little bit more detail about it when I get into custom vision in a moment as well. So we've got about 35 minutes left, so that seems about right. All right. Just let me give you a couple more examples just on the accessibility front. Another sort of example of artificial intelligence being applied in here is with Microsoft Translator. You might have used Microsoft Translator in Skype if you're talking with somebody or chatting with somebody by typing in another language. It'll automatically translate what you type into Japanese for your Japanese friend, and then when your Japanese friend types, it'll translate it back into English just for you as well. That also now also works with speech. So if you're talking with a phone call, it will do real-time translation from your language into their language. But again, this is one of the another example where something that was designed for one audience, in this case, vision impaired people, has really benefited everybody. And sort of one example here was MIT College of Technology. Now when they do their lectures, they have automatic transcriptions of their lectures from English into English to help the vision impaired people. There are a lot in those classes. But it's turned out it's helped all of the students because they now have transcripts of all their lessons they can go back and search and get information for as well there. But what I wanted to talk about here was an example of what I called enhanced AI earlier on. Sort of taking an existing AI system, and in this case it's an AI system for transcribing voice into English, and being able to enhance that with additional data to make it do better. And the example I'm going to give here comes from the Microsoft Build conference back in September. I was in the audience for this one. And I just thought it was really powerful, so I just grabbed a little clip from that to show you. But let me play it right here now.
What we are demonstrating today is a prototype of the adaptation of the acoustic model to my voice, which is impacted by my deafness. In the community, we call this deaf voice. This enables the speech recognition to be almost as good as for people that are not deaf.
那么，系统现在已经完全根据您的需要定制了吗？
Yes, from my voice to my vocabulary for speech recognition and translation. I could even create a custom text-to-speech voice in any language.
All right, so that was from a lecture at this Build conference. The guy there on the left is Harry Shum. He's the head of Microsoft Research. On the right there is the Skype Translator app running in real time. So as Harry speaks in Chinese, it's automatically identifying his voice, translating from Chinese into English, and presenting the English captions on the screen for everybody to see and for Jonathan to see as well. Brian, rather, to see. So that's just standard Skype Translator functionality. But the guy on the right there is Brian Traeger. He's one of the engineers out in Redmond, works on Skype Translator, and he is deaf. And he has what in the community is called deaf voice. He's never heard his own voice. And so as deaf people in that situation speak, they can be very hard to understand because there's just no training in how to pronounce things. And if you've ever had to try to have a voice conversation with a deaf person in that situation, they can understand you fine. They can lip read very well. But for you to understand what they say, if you don't understand sign language, can be very different. So what Brian did was he augmented Skype Translator with some data about his own voice. He spoke some words that were presented to him by the translator system using his own deaf voice. And through that, it was able to adapt the existing AI network that did the translation and transcription to understand the way that he speaks, and to be able to just transcribe him directly as well. That's a process of only about half a day or so of training. But using sort of the underlying sort of network and then augmenting it with his information, you can see that the transcriptions that were generated from his voice, they weren't perfect, but they were certainly enough for people to understand him very well. And this is a great example of something that, you know, if you needed to build that from scratch, like Brian would have had to spend weeks in a studio, you know, reading every possible word the translator might have needed. But because he can sort of build on the existing technology that was learned to do regular transcriptions and translations, he only needs a few examples of his own voice to get pretty good transcriptions, as you saw just there. That's an example of this enhanced AI. This example in particular is custom speech, but just with a little bit of augmented data, you can adapt these existing AI tools to learn new things, and it works pretty well.
It seems like that one's a feedback loop where it helps you improve pronunciation.
So the example, it's open to a feedback loop to help him enhance his own pronunciation because he can't hear his own voice. Yeah, I guess so, because I guess when he knows the transcriptions has mistakes, he could maybe sort of identify things. Although this is completely off topic, but I've seen other examples there are now cochlear implants that deaf people can get that provide some vibration feedback. So even if they can't hear, they do get enough of that feedback loop that it markedly improves spoken voice. It's really amazing the way it works. Okay. The last example sort of in this journey, stages of AI, I think that I want to talk to you about here is bespoke AI. And this is building things from scratch. And the example I wanted to give here comes from the Seeing AI app, which has a tool for reading barcodes. And you might think that's pretty simple. You know, we've had this for 20 years. And in fact, blind people can buy barcode readers. They cost about $1,000, and you can scan a product, and it'll tell you what it is. But the problem is for a blind person is you don't know where to scan. You don't know where that barcode is. And so what they've built into Seeing AI is a little tool that you can put the product in front of the screen, and it'll help you scan it, as you'll see here. It's probably easiest showing than said. One more click, maybe. There we go.
Processing. Expo low odor dry erase markers with chisel tip 4%. Assorted.
So this is an example where the pre-trained AIs, vision APIs, would not have held because they're not designed to detect barcodes. And even if they did, all it would say, like, this is a barcode, but you need the numbers off of the barcode. So what they had to do was build from scratch a custom AI system that could detect a barcode in an image, and not just a barcode like right up close. It's got to detect it, you know, if it's less than 0.5% of the image. This was a trained AI using CNTK, which is Microsoft's own TensorFlow-like network, just trained on lots and lots of examples of barcodes in different orientations and so forth. It's also got to run really fast, and it's got to run on the phone. Like this is an example where you can't take a frame of video, send it to the cloud and back again, and get a beep at the right time. So this is actually an example that's implemented in Core ML. It's exported from CNTK, runs on Core ML directly on the phone at 24 frames per second, which syncs up with the video, and so it beeps as soon as it sees a barcode, and then you can zoom in close enough so that it can read the numbers, and then it just does a database lookup to get the actual product thing. So that's an example of bespoke AI, where you have to build something up from scratch, and also an example where you have to deploy it directly onto the device to make it work. I'm not going to go into this today. We don't have enough time, but of course, you know, the basic process for doing this is the typical data science process: gather data, build and train models, deploy it onto an application, or in this case, a device. Microsoft has lots of tools to help with that. This is my plug for the session. Azure Machine Learning is a framework that runs out of Python that helps you with the process of building these artificial intelligence models, trying out lots of different model types, trying out different hyperparameters, recording all the results, optimizing hyperparameters, comparing models, lots and lots of nice things about that. But the basic idea is designed to take things that you develop on your own laptop, then scale up to training in the cloud with, say, thousands of servers. And then the next step, of course, is then deploying those models out into applications. And you can do that on the cloud, of course. You know, you can pop it into a container, the model you develop, like that barcode reader, and run it in our Kubernetes service or IoT Edge. But I think the really cool thing is you can put it into any container host. So the iOS example did not use containers, but the principle is the same. You can export your custom model into a container and then run it on a device of the next, on the Internet Edge or anything you like that runs containers. And these days, a Raspberry Pi can run containers. Anyway, didn't really want to go into the details of that, but just again, to give you this context of the 3 levels of AI: pre-trained AI through APIs, enhanced AI, where you take those APIs and add a bit more of your own data to make it work better, and then bespoke AI, where you build these models up from scratch with lots and lots of data. All right, last example. Should fit right into time. Okay, this last example comes from a third AI for Good program called AI for Humanitarian Action. It was just launched a couple of months ago. It's a $40 million program, I believe, to support disaster recovery, address the needs of children, protect displaced people, and promote human rights. Again, there are several different programs around them. I'm not going to go into details here just in the interest of time. But the one I'm going to focus around here is around disaster relief. So organizations that respond to earthquakes, famines, crashes, those kinds of things, improve their response and recovery programs, detects early signs of disasters, help responders better target aid, and help the beneficiaries during their times of crisis. And the specific example that I'm going to give here is around disaster search and rescue, and with an open source project that we have from Microsoft called AirSim. The basic problem is this. I mean, think of that Lion Air crash just last week. So an airline disappears from radar, it crashes somewhere in the ocean, they don't know where it is. And you might think it's pretty easy, you can just send a plane or a drone to search the area and try and identify, plane wreckage. But, especially if it's been a little while since it happened, it actually turns out that from the air, it's actually quite difficult to distinguish, a piece of aircraft from something just as simple as a breaker, a wave on the ocean surface. And so what we wanted to do was try and figure out a way to automate this process with AI. And you could send out, dozens of drones with an AI system to scan the ocean and then automatically alert people when they find wreckage in their vision systems. But how do you train a drone to recognize wreckage in this way? Especially when this is a situation where you kind of intrinsically don't have a lot of data. There are not a lot of examples out there of airline crashes, and every disaster response is different. And so the solution that we came up with of providing the data to train the systems is AirSim, and I'll explain it in this video.
For a real search and rescue scenario, the biggest problem that we have in these types of, high risk, high danger scenarios is that you're actually not able to go and physically get that training data that you need to use to train the model. AirSim allows us to get synthetic data to do that. What we saw is there's a need to put AI on edge devices, such as this one that I've got here in my hands. We dreamed up this whole scenario that you see behind me, which is a search and rescue for stuffed animals. We took pictures of this entire field and all the animals, and we 3D modeled it in AirSim using the Unreal Engine. We got a 3D environment. You're able to fly a simulated drone around to generate training data and use that to train the actual AI model to recognize the animals. Prior to the latest and greatest that we're releasing at Build, we weren't able to actually complete the scenario at all. What we see now is running AI models on edge devices where you're not in, a cloud data center or not on premises with large servers is actually reality today. And out of AirSim, we exported hundreds of images of each of the animals and imported them into custom vision and used that to train the actual AI model to individually identify each of the animals based on that synthetic training data. We export it out of custom vision into a TensorFlow format model and Dockerize it and then upload it into Azure IoT Edge and Hub. And from there, it's able to communicate with this device, which is running on the drone and running the actual AI model on the drone. Whenever it does identify one of the animals, it sends a message to Azure IoT Hub. And from there, you can pretty much, do anything to process those JSON responses or messages that land in Azure IoT Hub. Developers can learn on the latest and greatest AI technology and how to bring AI to the edge. You can download the dev kit on AI School today.
So the basic idea there is given that, we can't get lots of real world examples of aircraft wreckage, what we could do is model aircraft wreckage in a 3D environment, a simulated environment. In this case, Unreal, which is the same game engine that drives Call of Duty and a bunch of other things. But you could set up this 3D environment and then fly essentially a virtual drone through that environment, capture virtual images from lots of different angles, and then feed that into a computer vision system to enhance the way we do that detection. So Sonia did that with stuffed animals, which she actually did in a real field and trained a real drone to identify those. All of the code behind that is available on GitHub. It's actually a huge project that's gotten a lot of adoption. You can see sort of the number of commits and contributors there. But it's an entire system that you can use to set up your own 3D environment, run the simulated drones to collect data from lots of different angles, build a vision system on top of that data, deploy the vision system into a real drone, run the real drones and see how that works. And obviously we don't have enough time to go into all of that today. So instead I'm just going to focus on one little part of that, which is the custom vision thing. With this data you collect from the virtual system, how do you enhance one of our vision APIs to detect these new things? In Sonia's case, it was stuffed animals. In the real world case, it's airline wreckage. I'm not going to do either of those things. I'm going to do hot dogs with customvision.ai. I'm going to use a service called Microsoft Cognitive Services, Custom Vision, which is basically a way for you to provide your own tagged images of wreckage, or real world or simulated, whatever, and then create a classifier which will tag new images according to the images that you've already provided. Probably easier if I explain it in detail. But before I do that, this is probably a good opportunity to actually dive down into some of the mathematics behind how, first of all, computer vision systems work, and then how transfer learning and custom vision systems work. This all the way is actually taken, this is taken from a good friend of mine, Brandon Rohr. He has a great website and a great blog, which if you are interested in understanding the mathematics behind how these things work, he explains it better than anybody that I know, so I thoroughly recommend checking that out. But I'm going to take my own attempt at explaining this to you about how computer vision systems work. So the API we saw already. Like we could put a picture into the API at this end. Something happened, and at the end it gave us a bunch of tags and confidence associated with it about what types of images, what types of objects it detected in this image. Well, how does that actually work? And it works with deep neural networks, specifically. Well, first of all, a neural network is something that's been around since the 50s. It's the only thing that deep there means. Deep does not mean profound. Deep just means it has lots and lots of layers. And by layers, I mean we push an image into this end of the neural network. It gets pushed into these. It gets copied into these first layers of nodes. And at each node, a mathematical operation is applied to the pixels in that image. I'm not going to go into too much detail about that, what it is, because I don't have a lot of time. But fundamentally, you can think of it as a filter, like in exactly the same way as you have a filter in Instagram or Snapchat. You know, it's basically a little matrix that's applied over the rows and columns of that image. And, you know, I have a matrix which converts everything to gray, or makes things blurry, or identifies an edge. But it's some kind of a filter is applied at each layer of this neural network. And then the output of that filter, which, by the way, typically shrinks down the image by a pixel or two, is all passed into the next layer and combined. And then another filter happens. And then that happens again. Another set of filters get applied. Another set of filters get applied. And by the time you get down to here, the image, which has been shrinking down and down and down, is probably just 1 pixel in size by this point. And then you can combine together those numbers that represent a score, and you can interpret those scores to say the confidence that a dog is in the picture, or a confidence that a bicycle is in the picture, or the confidence that an apple. These categories are all predefined. So this particular neural network is designed to detect and can only detect dogs, bicycles, apples, and tennis balls. Got that? Now, once you've trained that neural network, and I'll get to how that happens in a second, you can give it a new image. And here's a picture of a bicycle. It runs the filters, combines, runs more filters, combines, filter, combine, filter, combine. And at the end, we get 4 scores for our 4 tags. The one that comes out the highest is bicycle. And indeed, that is a picture of a bicycle. So that's magic, right? So we can put an image in, it'll classify it correctly. But how do we actually get to that point where the neural network does that right thing? And that's the training process. What we do is we give it many examples of images where we know what the actual classifications are ahead of time because we've pre-tagged them. And all we do is we adjust the weights of these filters such that for every image we pass in, the correct score gets generated at the end of the network. And we, with many, many examples of these images, we adjust the weights accordingly so that for the entire set of images, the right set of weights come out at the end. And I say just, of course. You know, that's a pretty complicated optimization process. And if you go to AI conferences, you'll have a lot of people talk about back propagation and sampling and scoring and all kinds of things. It doesn't matter. this kind of stuff is really irrelevant, at least to me, in the sense that it's just an optimization problem that'll probably be completely solved in a year or so. All you need to know is the optimal set of weights have been selected such that it minimizes the discrepancy between the classifications of the images that were given and the classifications of the images that were generated. And this has been the subject of research for the past 10 years. That ImageNet website that I showed you earlier on has been driving a lot of this research. People have been developing instances of those neural networks to classify all the images in ImageNet. Just 8 years ago, the best they could do was about 72% correct classification. Now it's like way above 97%, in the sense that people really consider this problem solved at this point. You know, you can build a neural network that will correctly classify a set of images and a set of classifications at greater than sort of human level capacity. And in fact, ImageNet contests have moved from these 2D problems into 3D problems now because it really is considered solved. But I'll reiterate, this only works for the set of classifications that the network was already designed for. Our network was only designed to classify dogs, bicycles, apples, and tennis balls. But what if we want to classify something else? Now, of course, we could start from scratch. We could get a whole new set of images that includes our new classification, say bananas, but that's really hard. And it turns out there's a shortcut that we can do. Let's just strip off that final layer from that neural network. And so that what we get now is not a set of classification scores. We just get, you can consider these just as numbers for the purpose of this discussion. We just get a number, F1, F2, F3, F4, F5, F6, F7, F8. We get 8 numbers when we pump an image into the end of this pre-trained neural network. Well, what kind of use is that? Well, we could take a new image and pump it through that network with the missing layer. We could take an image, say, of aircraft wreckage. We pump this image through. It's going to get us 8 numbers at the end of the day. And we have associated with that 8 numbers a binary value. Is it wreckage or is it not wreckage? And we could do that with a different image of wreckage. And we could get another 8 numbers and a binary value. And we could do it with an image of waves, for example, to get another set of images. So what we're building up is our own data set. 8 numbers and a binary classification. 8 numbers and a binary classification. What does that sound like to you? Well, that's logistic regression. We could just keep on doing that as many times as we need to until we get a good logistic regression model that lets us classify waves from wreckage. And it turns out that works really well. We're not really sure why, but one of the ways you can think about it is that each of these sort of nodes at the next layer back have already been trained on a bunch of other images, dogs and bicycles and apples and so forth. But intrinsic in these trained weights that have sort of been optimized here is that this last layer is capturing something intrinsic about the image that goes in. Again, we don't really know what it is, and it depends on the individual network. There's a lot of research trying to understand this better. But you might imagine that this F1 number represents the greenness or the blueness of the image. This F2 number might represent, how many circles are found in the image. This F3 might represent some other intrinsic value of the image. And of course, in a real network, there are many thousands of these. But it turns out that we can just pump a brand new image of a completely different classification, extract out some intrinsic features of that image, which you can then use through regular regression techniques on our new classifications. Now, again, I've made this super simple. I've elided many, many details. And in practice, it's not really regression. It's just one-layer neural networks. But the principle is the same. We can use the information about detecting intrinsic qualities of images from a trained network and use that to classify brand new images with custom vision. So here's another example of putting another piece of wreckage in there. I'm not going to do that with waves for reasons I'll explain in a minute. I'm going to do this with hot dogs. I've got a bunch of images of hot dogs, and I'm going to try and now the API is not designed to classify hot dogs, but I can now train it with a bunch of images of hot dogs and things that are also kind of look like hot dogs but are not hot dogs to do that, as we'll see in a minute. By the way, does anybody know why I'm doing this? Has anybody seen Silicon Valley? I'm not going to play it right now, but I do have the little video clip. I might play it later on that just kind of explains the thing behind this. But let me just jump into our last bit of the workshop and show you how this works in the minutes I have remaining. All right, so I'm going to go, first of all, to skip over this. First of all, I'm going to go to customvision.ai. And you can do all of this directly through the web-based interface. I'm going to do it through an API. But I did have some data I was trying to use for this with images of things that are not ocean, so boats and whales and things like that, and things that are ocean. And just with these 100 or so images, I could actually train a classifier that actually does pretty well, about 90% classification. If I give it a brand new image, one of the existing images rather, has about a 10% false negative rate and about a 10% false positive rate with the existing images that we have. The problem is I didn't have any additional images of waves or boats or things to work with. So I'm going to do something different with hot dogs. And let me go ahead and show that right now. Again, I'm going to do this from R. One of the first things I need to do, where is my number 3? Did I not open it yet? Okay. Okay, so first thing I need to do is create keys again for custom vision. So let me go ahead and do that. Custom vision's in beta, so you need to search for this one. All right, custom vision preview. Create. All right, so AI for good. Custom. All right. Why isn't it giving me an option? All right, something is, there we go. Not giving me an option for that. All right, I don't know why that's happening. Let's try this again. Resource groups. Okay, I'm fine with that. Resource groups, AI for good. All right, let's add a resource. Custom vision. Custom vision preview. Create. There we go. Don't know what happened then. So I just want to choose the free tier. Okay, created my resource group. All right, so now I have some new keys. Let's go back to my resources. All right, so what I was doing here is I just to grab my keys for my vision. Actually, no, it's custom vision I wanted. AI for custom, there we go. So there's a key that you need for the predictions. For the training rather, and that's my training key. Go back to my keys file here, edit that. Okay, and lastly, I need to get the prediction key as well. All right, I think we should be good now. All right, so with those keys in the system, we can now run it. So again, we're just using the HTTR package. I'm also using the JSON Lite package in R now to interpret the JSON that's going to come out. Same thing again, just grab the keys from my file. That all looks good. All right, so this is another example when we talked about sort of using an AI network that's related to the data that you're using. The custom vision system actually has several different underlying trained networks you can use. They've been trained on different sets of images. And in particular, there's a domain that's been trained on food. So it's specifically designed to detect different kinds of food. That's going to work well for us. So I'm going to use that specific domain. I'm rushing a little bit here just for time. But this is just to set up my project in R. You can try this at home as well. All right. The next thing we need to do is to define the classifications of objects that we want to detect in our custom vision. So we want to detect hot dogs. I could do it just with pictures of hot dogs and it would work okay, but it actually works a little bit better if you provide what we call a negative set. So images that look like hot dogs, but are not hot dogs. So I'm also going to provide images of things like burritos and tacos, stuff that could potentially be mistaken for a hot dog, to make a better discrimination in my classifier, which will make it work better for detecting hot dogs. All right, so now I have to find 2 tags. So what I'm going to do now is go back into customvision.ai and refresh all my different projects that I have here. And one thing you see is just created this one, AFG hot dog, this one, yeah, that was the one. All right, and you can see there's nothing in it, but it does have 2 tags defined, hot dog and not hot dog. So the next step is to upload images that represent each of those 2 tags. And you can actually just drag a folder from your desktop and do it directly through the UI. But in fact, I've already got a list of URLs that I have in a file. And so I'm going to use R to iterate through those URLs, grab the image, then upload it into customvision.ai for me. And that's actually this whole next step here in the R code, is to read in 2 files of images of hot dogs and images of not hot dogs, and then a function upload URL I've defined, which is going to use the API to upload them into the system, and then report back. So if I run that now, it's going to take a little while just to download those images, and it's reporting back false, which means there was a problem with one or more of the images, and that's not a surprise to me. This list I generated about 6 months ago, and of course, as you know, bit rot is a thing, so some of those URLs are no longer accessible. And there's also some other problems which I'll identify in a second that I need to fix. So if we go back into customvision.ai now. Okay, and these are the images that I just uploaded. I'm going to just filter them by the 2 tags. So click hot dog here. So these are just the images of hot dogs. I got most of these from ImageNet. And you can see they all are pictures that have hot dogs in them. Sometimes there are people in them. Sometimes there are multiple hot dogs. Sometimes there's one. Sometimes there's devices. This one here, though, is actually a picture of sausage rolls. So I need to fix that. I could have fixed that in my source data, but what I could do is just add not hot dog as a tag to that one. There we go. And here's another problem that is typical when you're working with images that come from Flickr. If somebody deleted the image or it's not available, you get not an error, but you get an image that says this photo is not available, which is going to cause us problems in my classification. So I'm going to go ahead and delete that one. Yes, delete. All right. What else? There's another image. So that's not really a hot dog. There's another puppy in here somewhere, I'm pretty sure. Let's delete that one. It's funny, like every time I do this, it's a little bit different just with the images that are actually available that come through and not. And I guess with Flickr just about to go down, this is going to break soon now that I think about it. Flickr just changed it so you can only have 1,000 images in there. I think there was one more thing I need to delete somewhere. All right, that's close enough. All right, so now we have not very many images, just 60 and 170, so that's like 160 odd images. But this is actually enough to actually train a classifier that, given a brand new image, can detect whether something is a hot dog, or if something is one of these food items that's not hot dogs, or neither of those things. So let's actually go ahead and do that in R. I can actually do this directly from the API just by clicking the train button up here. But I'm just going to launch it directly from R so you can see it. All right. Something has gone wrong somewhere because I got 2 different numbers here. Let's see what happens. All right. Let's go ahead and train this project. All right. I've got a function that's just... So training is asynchronous. It takes about 30 seconds. So you can see it's training right there. And as I keep on running that function, eventually that's going to switch over to completed. This is a good opportunity for us to go over into custom vision here and have a look at the performance. You can see iteration 1 is busy training right now. All right, and you can see it actually does pretty well. This is our false positives. So only 4% of the things that are not hot dogs in the data set get classified as hot dogs, and 10% of the things in the data set that are classified that are hot dogs are classified as something that is not hot dogs. But that's dependent on a probability threshold. So when I give it an image, it gives me a probability back for each of the classifications. And we can set that threshold wherever we want. We can make it higher, which will give us fewer false positives, more false negatives, and we get it lower, which goes the other way around. Now, whether false positives or false negatives are more important is something you should really think about. If this was an application for detecting lung cancer based on images, for example, you would probably want to have very few false negatives, but you'd be fine with false positives because that would be followed up by a more clinical exam. In this particular case, we don't really care either way, hot dogs versus not hot dogs. So I tend to choose a probability threshold that tends to balance my false positives and false negatives. So looking at about 35% or so would be the threshold at which we'd accept a classification that the vision system gave us. So now to wrap up, if I just check back with R now, it should tell me that this iteration has finished. Indeed it has. All right, and now I can write a function which will do the classification of a brand new image. There's a prediction endpoint, so it's a different URL and different key, which is why I needed 2 keys earlier on. I write a function to do that. All right, almost finished. And now I can run my prediction function on 2 of the images that were in the classification set, hot dog 1 and not hot dogs 1. All right, so correctly classified that as a hot dog. That's good, but that was in the training set, so we'd expect it to. Probably more interesting what happens when we give it a brand new image that it's never had before. Here's some examples of both. We can try out those 2 there. All right, so there's an example of something that is a hot dog that it correctly classifies as a hot dog. All right, I rushed through that a little bit for time, so let me just wrap up real quick. All right, so everything we've seen, just 3 examples of using artificial intelligence for good. If you want more information about the specific examples I showed you, or you would like to apply for a grant, all of the information is about here. I didn't leave any time for questions, I'm sorry, but I will hang out here if anybody has any questions and happy to chat. But thanks everybody for coming once again, and thanks for your attention. Please.